So I'm going to continue talking about closed strings and operads. So last time we saw operads. For example, and so we had these qualifiers: non-unital, non-symmetric. Is that good? For example, the associative operad, and the one we were particularly interested in, which was the homology of our Deligne-Mumford compactifications of moduli spaces of genus 0 Riemann surfaces. So in fact this latter is symmetric, or it makes sense to regard it as a symmetric operad. Which means there's an action of the symmetric group on this space, which is permuting the n marked points, which are not regarded as the output, and algebras over this operad respect this symmetry. So you saw this the genus 0 Gromov-Witten invariants equip.
Can you clarify that last sentence?
What they respect.
Is this a statement, so to speak, in pure algebra?
Yes.
That an algebra over this operad automatically respects the symmetry?
It should be a definition that an algebra over a, if we're working with symmetric operads, okay.
Okay, it's not what it, you don't mean exactly what you mean.
Okay. Are required to. Okay, so we're introducing this qualifier symmetric, which changes what we mean by an operad and by an algebra over the operad. And the genus 0 Gromov-Witten invariants equip the cohomology of our manifold, coefficients in this Novikov ring that we defined previously. With the structure of an algebra over this operad. So we recall that this meant we have maps from these spaces into Hom from cohomology n times to itself. And this, we recall that the way you get this map is by taking a homology class in here, counting J holomorphic curves with constraints prescribed by classes in cohomology, and with the domain constrained by the homology class that one takes here. And the fact that this does give rise to the structure of an algebra over this operad was merely an expression of the fact that counting nodal curves like this is, with some constraints on the homology class in the two components, is the same thing as counting guys like this together with guys like this together with a point constraint that these marked points here coincide at that node. So that's all this was really saying. We then saw and sorry, there was this symmetry requirement, which basically says if you permute the marked points in here, then these maps are equivariant with respect to that action and permuting the inputs over this side. So there's a morphism of operads. So the associative operad is the same thing as the degree 0 part of homology of these spaces, just the point classes, which of course sits inside this whole space of this whole operad, including higher degree homology groups. So in the same way that a homomorphism of algebras from R to S means you can regard any S module as an R module via that map, a homomorphism of operads means an algebra over this operad can be regarded as an algebra over this operad via this map. So this equips cohomology of a manifold with the structure of an associative algebra. And this was called the small quantum cohomology. Okay. Which we denoted like that. But somehow this is not seeing all the higher, or all of the structure of an algebra over this operad. So we want to see more of the algebraic structure that we get out of this. So we denote just using round bracket sub k the map. Okay, I'm going to stop writing lambda naught coefficients. We're going to denote this bracket symbol the map corresponding to the fundamental class. All right. So that's the top degree class, the fundamental class of this guy. So now for any v in the cohomology of M, define, and in classes alpha and beta, we're going to define a new product. This is going to be called the big quantum cut product, and it's parameterized by this V. And it's this sum of all k greater than or equal to 0 of this bracket operation where we start with alpha and beta and then put as many V's in as we need. And we divide by k factorial. Now, of course, we need a reason why this sum should converge. In general, it won't. So we'll reformulate things slightly. But leaving that for the next board, let me say a theorem modulo convergence that this star V is an associative product as well. And the proof goes in exactly the same way that the proof that this small quantum cohomology algebra product was associative. Associativity
theorem modulo convergence or proof modulo convergence?
Sorry, what's the difference? What do you mean?
You're saying the theorem's
I'm saying that this is not yet defined. In a sec, I'll give the proper definition, and that will make this a theorem. I mean, there are various assumptions you can make on your manifold, for example, making it monotone, which mean this actually converges honestly, and then you don't need to worry about. But we want to do a general proof, and I don't want to get into those technicalities. So we saw that associativity, the small quantum cut product, was really saying that these two points in degree 0 chains on M bar 04 are homologous. So this was sort of like alpha this was alpha and beta, the first two inputs, and then this was gamma and the last output, and then this one over here was alpha quantum cut product, beta cut gamma. The second and third inputs came in here. So this is what we saw was the geometric way of understanding associativity of the small quantum cut product. So we want to pull this relation back to homology. Via the forgetful map which just forgets all of the, M bar 04, via the forgetful map, which forgets all of the marked points but 4. Then we have, morally the fibers over these 2 points are then also homologous, and we get a relation in this homology space.
I'm not sure what's being pulled back. In my naive world, it's cohomology that pulls back.
So you need to Poincare dualize and then pull back, and then Poincare dualize again. You have a does that make sense? I mean, you take whatever cycle you have, whatever chain you have, Poincare dualize it, pull it back to cohomology of this space via the forgetful map. Then you get some relation between two cohomology classes, which you then Poincare dualize.
Except you were in chains, not in cohomology, for instance.
Yes, but I mean, you can still get a relation in this way. I mean, up to homotopy is okay, because what we finally want to get is a relation in homology of this modulo space. I mean,
you're not claiming they're the same chain. You're saying
okay, yeah. Oh, all right. Yeah, sorry. Okay, yeah, I had no need to say anything about chains. I should have just said homology the whole way through. Sorry about that. Okay. Or draw exactly the same pictures. And now just put arbitrarily many marked points labeled by V in here. And look at the same moduli space of curves, but where now you're inserting a whole bunch of V's in here. And it's the same as this argument here, except you're just putting V's in wherever you can. So to deal with non-convergence, we have to work in a formal neighborhood of the origin. Okay, so rather than saying you can actually choose some V and get an honest product like this, you say instead star V equips this space homology of M, coefficients of lambda naught, formal power series in cohomology of M, equips this.
In your initial H star of M before the tensor sign,
Yes.
the coefficients are lambda 0 or not?
Yes. So we could also write lambda naught here, and this would be tensor over lambda naught. So this product equips cohomology of M with coefficients in this formal power series ring over lambda naught with the structure of an associative.
I'm sorry.
Yep.
The second H star of M, the one inside the double brackets, what are
Yes.
its coefficients?
Still lambda naught. Yes.
Everything.
Yes. I mean, we're just, everything is working over lambda naught. So now we find a formulation in which, since we're working with formal power series, this sum here actually makes sense, and that theorem modulo convergence becomes an actual theorem, that this space becomes an associative algebra over this coefficient ring. Okay.
Maybe you lambda naught double bracket something means what exactly? I mean, if explicit thinking.
Yes, exactly. A completed group ring where, I mean, if
I mean, so,
If-
you know, what's lambda naught double bracket lambda naught? That's like the base case. I mean, I'm really confused.
this would be the same thing as adjoining one formal variable, which is
Are you thinking of the second cohomology in that tensor product just with lambda 0 coefficients or just with,
this one here.
yes, or just,
Yes.
I mean, if the second
Yes,
one were
with lambda
integer
0.
coefficients, I would maybe think I knew what you were talking about.
Well, I mean, if we were,
I mean, already,
if we're just working over a,
coefficients and lambda zeros already is kind of a formal gadget. But you're not asserting that.
no, I mean, cohomology with coefficients in lambda 0 is, I mean, this is not so horrible. I mean, this is, I hope I'm not, since this is a finite dimensional vector space, and then we're just tensoring over C with this ring to get,
Correct, which is like a humongous super
It's-
duper power series, right?
right,
Fractional things.
yes.
So,
But it's a
I mean,
free module over this thing.
But I mean, a conceivable statement would be, so, in this sort of baby case, just think of lambda zeros itself, formal power series in one variable, right? So an element in the, whatever, H star with coefficients in lambda 0 is a power series whose coefficients are usual cohomology classes. And it's certainly plausible that if you take two such things and do this operation, then the output is a formal power series with usual cohomology classes, and there's no problem about convergence because the coefficient of t to the zillion is just a finite sum. But you're not saying that's the case?
Yeah.
Yes, you're not.
Yes, I am saying that's. Wait, so,
But then
sorry.
why do you need, I mean,
Wait, okay, sorry.
you guys are committed.
Sorry.
What's wrong is that you have H2 twice, right? You have H2
That's true, but I would rather keep it like that.
I mean, maybe that's the confusion.
Okay, I mean, is that the confusion? I mean, what Ralph is saying is that somehow the formal variable in lambda naught, in some sense, corresponded to the symplectic form, which also appears in here. So we're seeing it twice. And this is true, but
no, I don't
but
think
that's
so. I mean,
how I want it
I
to be.
think my confusion is either much deeper or much stupider.
Why
So-
don't you give us a formal definition of this lambda naught double brackets 8? Well,
I mean,
Double brackets a free lambda naught module. Okay. I mean, Okay, well, the definition I would like is if so, if you choose alpha beta is a lambda naught basis for, say, this no, this is not a good definition, sorry. I mean, all it's saying is we're adjoining as many variables as there are lambda naught generators of this guy. All, you know, everything is being done over lambda naught.
If I chose a different lambda naught basis, how would I identify the ring?
We take the group ring and complete up the augmentation idea. So
that sounds right, but I mean, I mean,
So you're taking the symmetric powers of the module
yes,
and taking the direct product over all n.
yes. Sorry, that would have been a better way of writing the definition. Sorry.
Just the ring for whose formal spectrum is the formal neighborhood of zero of that affine scheme.
That's another way of saying, yeah, the formal neighborhood of the origin in cohomology of M, where this is really, of course, not a scheme over a field, but over this ring lambda naught. And we're taking the ideal in here corresponding to, yeah, I mean, corresponding to the origin. What does completing about that? I mean, has this made things better or? rubbed it out. It was
there. No.
yeah. I'm writing it again. Did I write that?
Just had the formula for that. You had alpha star beta over B.
Right.
Okay, so at some level, this whatever formal convergence business you're saying is some statement about these elements. But what statement is it? In other words, how do I see this as being in your lambda 0 double bracket thing? That's what I'm supposed to see.
So you should regard this as well. So given alpha and beta, so I think what I've done here maybe dual, sorry, but given alpha and beta, okay, so we're changing from this star V to some new product that's going to be associative. Okay. And this where, okay, so we so this should be the product S, all S greater than or equal to 0 of this lambda naught, free lambda naught module, so cohomology of M with the coefficients in this guy, S symmetric power, from that into lambda naught. So where I wrote up here, really, these should have been dual. I'm sorry about that. This should have been alpha dual, beta dual. So this is the dual basis. Of the dual module to n. Hom from n, hom over lambda naught from n into lambda naught. So this is, by definition, what this guy is here. And we're defining this by its action on a V. Okay, so how should I write this? Sorry.
You're just missing in your formula A star B. Now you have this B dual to the K. If you just write that, I think you get some formula.
How do we want to write this? All right, well, so I'm sorry, I'm blanking a bit. How do we want to identify these? So this guy here is some infinite sum. We're fixing alpha and beta. Okay. So this is isomorphic to that because this is a finite lambda naught module. So that commutes with this infinite direct product. So it doesn't interfere with the completion we're taking. And this is defined by its value on, for example, V1 tensor through tensor Vs is equal to this S plus 2 Gromov-Witten invariant, which is a symmetric in the inputs by the property I talked about at the start, that these Gromov-Witten invariants are symmetric in the inputs in that way. Okay, so what I'm really using is the fact that this what I'm really using is this isomorphism here, which holds because this guy is a finite, a free lambda naught module of finite rank. Okay. Did this help? Okay. Sorry if I'm not being very clear at the start.
Can you just like say some of what you just did?
So we should forget alpha star beta over V completely?
No, I mean, it's
infinitesimally small as specialize from this sort of formal algebra to V, then this star nu specializes to the star V.
that's exactly the idea. We wanted to define a new product parameterized by V by this formula, but we had this problem that it might not converge. For some manifolds it does, but I don't want to restrict to only those manifolds. So rather than being parameterized by V in all of cohomology of M, we instead look at a product parameterized by V in a formal neighborhood of the origin in cohomology of M. And the proper way to formulate that is as an algebra over this ring. So if we had polynomial brackets here, then an algebra over this ring would just be the same as an algebra structure parameterized by points in here. Because we don't have convergence, we have to take this completion, which corresponds to only allowing ourselves to work with V in a formal neighborhood of the origin. Okay. Other questions? So theorem these operations generate the operad homology of m bar 0 k plus 1 and associativity of this product star V is the only relation between them. In other words,
Formally star U is it?
yes, which I really only introduced for the purpose of explaining that. Okay, so this is due to Kiel and Kontsevich Manin. Okay, so
You lose no information by just considering this star V.
exactly. Star V contains all the information of all these operations parameterized by all the homology classes on these spaces here.
So this is somehow the sense that in SymS of some finitely generated module, if you know the S powers of elements, then you know that they span the thing. That's the point. So the K powers of linear forms span homogeneous forms of degree K. And that's why it's enough to.
No. This depends on the geometry of that space.
Huh?
It depends on the geometry of that space. What you're saying is why he only has to give this power series this way. And then, but here you need the theorem that that you know the cohomology of moduli space is spanned by the divisors, and the only equation you have is the pullback equation from 4 points. You need Kiel's theorem.
Were you asking about this theorem or about that formulation there?
I think I was trying to understand why, if you know what happens when you put V1 through Vs all equal to V, but you do it for all V,
Yes.
then you know what it is when V1 through Vs are any.
Then you're right.
Yes. Then
That's what I was,
yes, that's
that
correct.
was my aha.
Okay.
Understanding how we did this. Yes.
Okay. And maybe I should put an aside. You should think about this coefficient ring for our algebra with where the product is star V. Should think about elements of this as parameters on this extended symplectic moduli space that I spoke about in the first lecture. Okay, so recall tangent space to this moduli space was supposed to be cohomology of M containing H2 of M, which was the tangent space to the classical moduli space, which was by Moses' theorem, the tangent space to the moduli space of symplectic forms is identified with second cohomology of our manifold. But it's not quite that nice. We need to work over this lambda naught everywhere. If here we could put C, then this would really be, and if here we could put, if we didn't have to worry about convergence, we could just put C here, polynomials in here, and spec of this thing would just be cohomology of M. And that would be what's parameterizing our product star V. So this would be, this moral story would really make sense. But we do need to worry about convergence, and therefore we need to work over this Novikov ring and with this formal completion, these formal power series. So this moral story gets a bit obscured by that. But that's the idea. Okay. So now I want to do, show you something which maybe doesn't have applications later on for what we're going to talk about, but it's at least an explicit computation, which is very nice using this idea. And that is the Kontsevich recursion formula for genus 0 Gromov-Witten invariants in CP2. So cohomology of M just has three generators: the identity, hyperplane class, and the Poincare dual to the point class. Okay. And in particular, this coefficient ring for our quantum product star V. Oh, I should have said the name of that. This is called the big quantum cohomology. Okay. Contrast to the small quantum cohomology that we talked about previously. So here's our coefficient ring for our big quantum cohomology. So this one is dual to P, dual to U, dual to 1. And we suppose that the multiplication in our algebra, so there's our coefficient ring. There are our generators of the cohomology of M. Suppose our multiplication table partial multiplication table looks like this. All right, I'm going to mess this up if I don't follow my notes, but I should have. Okay. So I'm going to explain why this coefficient is 1 in a second. Okay. So I'm just going to use these three big quantum multiplications. And so I should explain right away why this point class doesn't appear in these two multiplications and only appears with a 1 in this quantum multiplication. Sure, I could write. Oh, yes, it is. So this is always true. One can prove that by looking at by an explicit geometric argument using holomorphic curves. So for P to be an output of a quantum multiplication, we would have to have alpha and beta, then a bunch of V's, and then this remaining point would have to sweep out the point class. However, this point can move around all over this sphere, and in particular, whenever the sphere is non-constant, it is always going to sweep out something of dimension at least 2. This can only happen if the sphere is constant. But now we know what constant spheres give rise to. They just give rise to the classical product or intersection product. In which, of course, U cup U is P, U cup P is 0, P cup P is 0. Okay, so that explains this first column in the multiplication table. Now, associativity says if we cup U cup U, then with P, it's the same as U quantum cup product, U quantum cup product P. Which means P plus AU plus B, quantum cup product P, is the same as CU plus D, which gives us EU plus F for P cup P, A times U cup P, which is, and then B is a multiple of the identity. That just gives us B times P. And on this side, we get that. So extracting the identity coefficients, we get this relation. F equals BC minus AD. Okay. So what does this tell us about Gromov-Witten invariance? So we're going to extract the, well, sorry, first let me say. Which Gromov-Witten invariance are we actually interested in on CP2? So the dimension of the moduli space is of degree D genus 0 curves. One can compute it to be 6D minus 2. So if we're going to get a moduli space of curves which we can actually count, we need to put some point constraints. And we need 3D minus 1 point constraints. To get a dimension 0 moduli space which we can actually count. So we let ND be the number of genus 0 points with 3D minus 1 marked points constrained to lie on the point class P in degree D. So just to remind you of the notation, that's what these three things mean. So we're going to extract the t to the d, p to the 3d minus 1 minus 1 of this f equals bc minus ad. So recall this t is a Novikov parameter that keeps track of the symplectic area of our curves, and this p corresponds to the point class p in our sort of extended coefficient ring here. So f was the coefficient of the identity in quantum cut product of p with p. So on the left-hand side, we get p, p. These are the inputs.
Is it big P's or little P's?
These are little p's.
They're all little P's. That's a little P.
This is a big P. This one here. Sorry, I'll try and make them more different. Okay, I'll revert to Australian, as that's how we write them. So maybe that'll help for this purpose. Okay. Yes. So this is coefficient, and it should be 0, 3d minus 1d. And the bars I'm putting to help you keep track of which ones in... All right, we've lost the formula, so... So I'm putting the bars to remind you which ones are inputs and which are coming from the sort of these as parameters in this big quantum cut product. And now there's a difference between the angle brackets and these round bracket ones, which is that this one was a Gromov-Witten invariant which lands in the coefficient field. So maybe I should write that as a reminder. So these angle brackets were the ones we originally defined as our Gromov-Witten invariants. The output is just a weighted count of curves. These were the ones where we dualized one of the guys in here and made it an output. And these gave us our operations, which had this nice operatic structure to them. So this corresponds to the coefficient of t to the d, p to the that, 3d minus 1 plus 1 times the identity in the big quantum cut product of P with P. We wanted the part that gave us the identity. So because we need to Poincare dualize to turn one of these guys in, this final guy, into an output, we make it the point class, because that's dual to the identity, which we want to be our output here. So that's the coefficient of t to the d, p to the 3d minus 1 plus 1 times the identity in this guy. That's this f. And that's equal to these two guys here, which are, I'm really going to run out of space. So we're going to have to expand these two guys in powers of t and p, and then do the formula for multiplying polynomials together. Right? So we need to add up over d1 plus d2 equal to d. And what it's going to give us is zero, 3, d1 plus 1, d1. And then this is going to be, I'll have to leave the thing with d2 over 3d2 minus 2 factorial. So that's B, C, those coefficients there, and then minus now we want A, which is the coefficient of U in U cup U. So we put U cup U as the input. Then we want the P to the whatever power, so we put all these little p's in here. And then the output, Poincare dual to U as itself, so we put another U here. And that's D1. And this guy corresponding to D. Over 3d2 minus 3 factorial. So that's what it means to extract this coefficient from this equation. Okay, so this is an equation in this coefficient ring of our big quantum cut product, and it's an equation, equality of two elements, and we're extracting this coefficient from that equation. And now we observe that if we put, well, maybe I can just draw a picture. If we count some number of spheres with some number of marked points constrained to lie on a point class, and one of them constrained to lie on a divisor, it's the same as the degree times if you forgot this point u. So why is that? Because if you've got some holomorphic curve, it's always going to intersect your divisor in d points, where d is its degree. So it's the same as counting these guys together with a choice of whatever marked point lies on the divisor. And there are d choices where d is the degree. So the reason that's useful is because it means that these guys in here can be turned into things of this form with only p's as inputs. We just have to multiply by the degree every time we take a u outside. So this is called the divisor axiom, Gromov-Witten theory. So extracting what it means, the number of degree d curves through 3d minus 1 points is equal to the sum of these guys. So where did this come from? This was because over here, these two guys have two u's in them that we need to bring out the front. And each time we bring a u out the front here, we pick up the degree d1. Here we've got two u's to bring out the front, so we get these two copies of d2. And then we have the second term there, which is minus 3d minus 4, 3d1 minus 1, d1 cubed, d2, n d1, n d2. So this is really nice because now we've got a recursion for nd in terms of lower degree curve counts. And we know n1 equals 1 because that's the number of degree 1 curves through 3 times 1 minus 1 is 2 points. That's exactly one line through any 2 points in the plane. So this allows us to compute n2 equals 1. So that's number of degree 2 curves through 5 points in the plane. There's one conic through any 5 generic points. N3 equals 12. N4 equals 620, and so on. So this was due to Kontsevich, the Kontsevich recursion formula. And these numbers also, as I understand it, weren't known to arbitrarily high degree before he came up with this recursion. So the moral is that in these kinds of algebraic structures that come up in Gromov-Witten theory and in other places in mirror symmetry, very often you have this big complicated algebraic structure, but a lot of it can be reconstructed from a small part. So this is kind of the extreme case where just knowing one curve count in 1 degree gave you them in all degrees, and it's also a theme of the rest of mirror symmetry that we'll talk about later on. Okay, I think that's the end of my time, so I'll stop there.
I have a
Sure.